Moving a flexible component from one position to another is a problem of interest in many engineering systems like overhead cranes, soft robots, and antennas. Often, while trying to move such flexible components, especially at higher speeds, undesired vibrations get introduced into the system. To avoid such vibrations, the motion of these flexible components must be planned carefully. In this work, we consider an Euler-Bernoulli beam which is attached to sliding cantilever joints at both ends. By applying a force input at one of the cantilever joints, we can move the beam from one position to another. A prototypical model for this beam is given by the Euler-Bernoulli beam PD. Here W is the displacement of the beam at the location x and at time t, and F represents the input force applied to the cantilever joint. The objective is to find an input signal to move the beam from a given initial position and bring it to a desired final position over a given time interval, and this must be done without introducing any vibration. This objective cannot be achieved by treating the beam as a rigid body and simply computing the input required to move the cantilever joint from the initial position to the given final position. Even if the input signal is chosen to be very smooth, undesirable vibrations cannot be avoided. So there is a need to design the control input very carefully to avoid such vibrations. We address this motion planning problem using the early lumping approach. In this approach, the length of the beam is discretized into endpoints and the spatial derivatives in the PD model are approximated. The approximate model that we obtain is governed by an ordinary differential equation or an ODE. Solving a motion planning problem for this ODE model using the flatness, we obtain a control signal Fn, and by taking the limit of these Fn's as n goes to infinity, we arrive at the control input F, which solves our problem. We applied this approach to the sliding cantilever beam and we were able to move the beam from a given initial position to a final position without introducing any vibration.